In 2018, Quaise Energy began with a mission to unlock a new form of sustainable energy, one that can supercharge a more viable energy transition and lift millions out of energy poverty. How? Superhot Geothermal. Superhot means more energy that produces more power. The hotter, the better. At 300 to 500 degrees Celsius, we can generate up to 10 times as much power as normal geothermal, which means more clean power on less land at a lower cost and faster speed of deployment. At this scale, geothermal reaches economic and power parity with fossil fuels. To unlock Superhot Geothermal around the world, we've been fast-tracking the key technology, founded in decades of fusion science: millimeter wave drilling. Superhot conditions are always found deep underground, and millimeter waves show the highest potential of reaching new depths at lower costs. Now we're laying the foundation for our first commercial operations: Superhot geothermal power plants online by the end of this decade. We are already leasing land for pilot plants in the western United States, securing commercial offtake agreements, laying out detailed subsurface development plans. Superhot geothermal is available everywhere on Earth if you drill deep enough. At Quaise, we've categorized locations into 3 tiers based on their geothermal gradient, the rate at which temperature increases with depth. A tiered approach enables us to strike the right balance between commercial speed and new technology deployment risks using the geothermal gradient. The higher the geothermal gradient, the easier it is to reach superhot conditions. Tier 1 is the immediate opportunity for our initial projects. These sites have the highest geothermal gradients, where temperatures of 300 to 500 degrees Celsius exist closer to the surface. For every kilometer drilled, the temperature rises by at least 60 degrees Celsius, making it easier to reach superhot conditions. While superhot geothermal temperatures at Tier 1 sites are accessible with conventional drilling, millimeter wave drilling improves the economics of accessing these higher temperatures. Tier 2 sites are where we scale up. With geothermal gradients of at least 40 degrees Celsius per kilometer, Tier 2 sites are only accessible with millimeter wave drilling, opening up a significant opportunity. Nearly 40% of the world falls into this category. Tier 3, a global solution. Tier 3 sites have gradients of at least 20 degrees Celsius per kilometer and are only accessible with millimeter waves to drill farther than anyone has gone before. They hold the key to making superhot geothermal a truly global energy source. Tier 3 sites could provide power to more than 90% of humanity. This tiered approach enables us to harness the power of superhot geothermal energy by prioritizing the most accessible resources first. The first stage of superhot geothermal development is getting a good view of what lies beneath. Tier 1 sites, or those with geothermal gradients above 60 degrees Celsius per kilometer, are limited worldwide and can only provide hundreds of gigawatts of superhot geothermal power for 5% of the world's population. Yet they are the prime locations to start unlocking the true power of superhot geothermal at minimum risk by leveraging widely available and mature techniques from the oil and gas industry. Geophysical surveys come first. They help us see below the surface, including magnetic, gravity, and seismic surveys, to map out important geologic features such as faults and depth to basement. This data tells us where to drill safely and how best to optimize the geothermal reservoir for maximum power output. A confirmation well comes second. It helps us collect data on rock type, pressure, natural fractures, stress in the rock, and confirm how far down we must go to reach our superhot target temperatures. It also helps us determine where and in which direction to drill injection and production wells to extract the thermal energy from the ground below. Conventional drilling is highly effective in sedimentary rock and at shallow depths. It uses a rotating drill bit at the end of a long pipe, called a drill string, to mechanically crush and grind through rock. And using a few well-known tricks in the industry like circulation cooling, drill string dynamics, and polycrystalline diamond compact bits, the range of conventional drilling can be extended to super hot conditions at Tier 1 sites to unlock hundreds of gigawatts and serve 5% of the world population. As we move into Tier 2 and Tier 3 sites, we use conventional drilling to start the job and switch to millimeter wave drilling when the conditions get so harsh that these tricks stop working reliably. Millimeter wave drilling is the most transformational drilling technology since the tricone bit was introduced to the world in the 1930s. While conventional drilling has taken us far, it faces real challenges at extreme depths. The equipment can't survive long-term in super hot temperatures, and the deeper you go, the harder it becomes to power the drill bit. Millimeter wave drilling changes the equation. Instead of relying on mechanical force, it delivers high-frequency electromagnetic waves through a waveguide transmitted from a surface-based gyrotron down to the rock face with minimal energy loss. That means fewer interruptions, less downtime at a lower cost, with the ability to drill in conditions that would destroy conventional tools. Millimeter wave drilling efficiently delivers energy downward, but what about removing rock cuttings upward? In conventional drilling, dense drilling mud is used to carry rock fragments called cuttings to the surface. But at great depths, mud circulation breaks down and becomes less effective. Millimeter wave drilling excels by using a purge gas system, where pressurized gas flow sweeps the small cuttings away from the bottom of the hole to keep the drilling zone clean and efficient. These advantages help millimeter wave drilling deliver more energy where it counts, avoid the mechanical limitations of traditional systems, and keep the drilling area clear. This is more than just a new tool. It's as consequential as peering into the atom, going into orbit, and mapping the human genome. And it can open the door to terawatts of geothermal power for the entire world. After millimeter wave drilling gets us to super hot rock, we need to make sure our work is permanent. Enter the world of super hot completions, building wells that endure against decades of relentless heat to deliver power without compromise. And they require no leaps into the unknown, just incremental innovations, leveraging everyday wisdom of mastering high heat and pressure. Billions of internal combustion engines and thousands of power plants around the world already thrive in realms hotter and harsher than superhot geothermal. In Russia and Germany, super deep boreholes even surprised scientists, proving that basement rock remains open and stable by its very nature. Superhot completions require zero quantum leaps. And to complete these wells, we're integrating proven techniques to ensure long-term durability, such as high-temperature cements to endure strong thermal loads, non-elastomeric zonal isolation solutions to reliably compartmentalize the thermal reservoir, and circulation cooling to temper heat during the most critical phases of well construction. We have closed all gaps for our Tier 1 sites. As we advance into Tier 2 and Tier 3 sites, the Earth offers new possibilities. Lower temperature gradients, greater fluid density contrasts, stronger basement rock become foundations for transformative innovation. The hydrothermal systems of the last century are rare jewels, but engineered geothermal systems are the future, transforming geothermal power from a one-trick pony to the workhorse of the global energy transition. In Tier 1, We begin with pressure-driven stimulation through compartmentalized completions to open pathways in the rock from the bottom up. Each stage then blooms like veins in stone, completed with proppants that hold pathways open, keeping the lifeblood of the power plant flowing for decades. As we descend into hotter, deeper tiers, the process shifts from pressure-driven to density-driven stimulation, with larger density contrasts between the injected water and pore fluid in the rocks. Density takes the lead. The deeper we go, fracturing becomes easier, not more challenging, and reduces the need for massive pumping fleets. Think of the wellbore as a thermal power transmission line. By targeting rocks at 300 to 500 degrees Celsius, water shifts into overdrive, achieving maximum heat transfer efficiency through 3 remarkable properties. Gas-like viscosities to enable easy flow through the fracture network, liquid-like densities to maximize heat transport, and extreme density contrasts between injectors and producers to minimize parasitic pumping loads. Under these conditions, each well delivers 10 to 100 times the output of all other forms of geothermal due to higher electric power conversion efficiencies and controlled geochemistry. Unlike hydrothermal systems, our geochemistry is engineered, not left to chance. Within an engineered reservoir, we control water chemistry to protect the system from scaling and corrosion, sustaining decades of peak heat transfer. Working in deeper, tighter formations also minimizes water loss, cutting replacement needs dramatically. The result? A system custom engineered for maximum power per well. Superhot Geothermal is a breakthrough that redefines global energy. By tapping Earth's deep heat, we'll deliver power at scales and efficiencies no other existing energy source can match. Lower temperature geothermal relies on niche organic Rankine cycles, converting barely 10% of heat to electricity. Superhot Geothermal upends the equation, enabling conventional Rankine cycles, the backbone of global steam generation, with powerful turbines and a mature supply chain. That means conversion efficiencies up to 30%, far superior to ORCs. At the surface, we'll channel the high-enthalpy superhot geofluid through a water-water binary heat exchanger, transferring the heat to a clean working fluid, avoiding impurities in the power plant while recycling the water. Co-locating near industrial hubs and demand centers further slashes transmission mileage, accelerates deployment, and cuts costs dramatically. Our Superhot geothermal power plants will also have a higher capacity factor than all other energy sources. Beyond electricity, Superhot geothermal can power high-temperature industrial processes, decarbonizing sectors that have no alternative today. It's scalable and resilient, turning Earth's deep heat into an engine for industrial innovation. This isn't incremental change. It's a generational inflection point to deliver abundant, reliable, and sustainable power for humanity.